So we'll begin it. We'll get to maybe a slide or two. So 6.2 is a continuation of 6.1. This whole chapter is on radicals. And we're going to look at properties now, okay? We're going to simplify expressions that have radicals in them. So let's start with our two rules first. The first thing to do. When you have the nth root of a product, you can write the nth root of one times the nth root of the other. So if I had, for example, if I had the third root of 27 times x cubed, I could think of this as the third root of 27 times the third root of x cubed. So I can break it up if they're multipliers, if they're factors inside. If it's a quotient, or if the two things are being divided under the radical, we can also break it up using the same exact rule. Okay, and then the cube root of 27 becomes 3, cube root of x cubed becomes x, and then we do that and that's sort of 3x. So the rule that we're applying is like a distribution, right? It's like you're distributing the radical to each. The reason I can do that is because the radical is really like a power. And if you remember your rules of exponents and your rules of powers, if I had ab to the n, this is really a to the n, b to the n. Right? And if I think about a radical as a 1/2 power, this is this, which is really this. And in turn, becomes this. So this is the reason for my rule and why it works. I can start with a radical and distribute it to both. Because I think of a radical as a 1/2, distribute the 1/2 of both of these, which is allowed, which is a product, and you get back to the same answer. So think about it as like a distribution, even though it's not. So think about it that way as a distribution. Take a look at the first one. Try part A. What does 75 break up into? It will work nicely if I distribute the radicals each term. What factors do 75 break into that are nice? Alex?
25 and 3.
I agree. So let's write it as root 25 times root 3. Write it as root 25 times root 3. And then root 25 is just what? 5. So your answer is 5 root 3. So the way I always approach these problems is I put the perfect square in the front and the non-perfect square at the back. And then take the square root of the perfect square and then carry over the non-perfect square. It's logical. It makes sense to do it that way. It doesn't matter whether it's variables or numbers, because we're going to see variables in the next part. How about part B? Can I do the square root of 8? Break it into 4 times 2. That's useful. And then 6, so I can break that into 3 times 2, but 3 and 2 are not perfect squares. So I can do this and come up with an answer, but there's another thing I could probably do to start.
Could you multiply it together?
Yeah, you could start by just multiplying the insides. Because if we're able to take 75 and break that into 25 and 3, we could take 8 and 6 and put it back together as 48. So part B could be thought of as negative root 48. But then what's 48 when I break it up? Good, 16 times 3. Some of you might be saying, it's 4 times 12. But 12 can be broken into 4 times 3. So it's really 4 times 4 times 3, which is what Helen just said as 16 times 3. Okay, and it's negative, sorry. It's negative the whole way through. The negative's on the outside, so I don't have to worry about it. If the one on the inside, I cannot take the square root of the negative number, it's imaginary. Let me show you just so you're aware of the other way. So I want you to see that you're not crazy in case you do it this way. You could do this. And then you could do this. I could put these two together as root 4. And then root 4 is really 2. So you get to the same answer if you break everything up. So you can start by breaking 8 and 6 into 4 and 2 and 3 and 2. Put the 2's together as root 4. Root 4 is here already as that. This root 4 becomes another 2. This root 3 is the only thing that carries down. I'm not going to simplify, giving us the exact same answer. Okay? Either way works. Same thing goes if you broke 48 into 12 times 4. Because yeah, this becomes a 2, but then 12 gets broken up into 4 times 3, and then that gets further reduced into this. So no matter what way we take this approach for part B, we'll get the same answer. I personally think that in blue is the fastest because it's the least amount of steps. But it might not be obvious to multiply 8 times 6, right? It might not be obvious. So you might want to take the other root itself. Okay? You can try C and D on your own tonight if you want, but just get on the homework for the... Alright, let's take a look at this one. So this is where we get into really honors algebra true course. Forget numbers. Let's go on to variables now, right? Variables. How about the first one? What do you think of part A? Regina?
I don't know if this is right, but we can do like the square root of 3 times square root of a times square root of b squared.
Can I write it like this? Is that all right? And I agree with what you're saying. Keep going.
And then you can cross out the squares on b. This is square root of 3a times b.
And we're going to write it like this always, okay? Now, one thing to point out, when you take the square root of a number squared, the answer is actually absolute value. And I'll explain why that is. Again, when you take the square root of a number squared, the answer involves an absolute value. More, do you know why this?
Yeah, it's going to have to be positive or negative.
Yeah. Think about x. X could have been positive or negative, right? Or b in this case could be positive or negative. So really it's the absolute value that comes out as an answer. How about 49? Not 49. How about part B with 49? What should I do with this? How should I break up y to the 5th? Because 49 looks pretty nice to me. That's probably going to go in the first part because it is a perfect square. Remember how we do this? The perfect stuff goes in the first part. The non-perfect stuff goes in the second part. What do you think?
Next to 49, you can put y to the 4th.
I agree.
And then in the other bracket, you can put y.
I agree also. Take a look. Make sure that makes sense. Get your spring balance, you know, y to the 4th that you took?
Because it's a perfect square. And also, y to the 4th times y is y to the 4th.
Correct. So she recognizes that y to the 5th can be broken into 4 and 1, 3 and 2, whatever you'd like it to be. Remember that the index needs to divide evenly into the power. Again, can you point that out? Write yourself a note if you'd like. The index, which is right here, what's the index? What number is really here? For a square root? 2. The index needs to divide evenly into the power. But 5 is not divisible by 2 evenly. So we break 5 into the highest thing that is divisible by 2 and whatever's left over. So take a 4 and divide by 2, it just becomes y squared. So this answer becomes 7y squared times the square root of y. Okay. Why don't I have to put absolute value around y squared? You got the first one, Laura. Can you do this? Why don't I have to put absolute value around y squared?
You mean around 7y squared or just...
Well, 7 is not going to be there, I can tell you that already, but why not around y squared?
Because if it's negative and you just multiply it twice and it just becomes a positive.
Hold on now. It's squared, isn't it? Y itself is squared. So by definition, it's going to be a positive number. So I don't have to put the absolute value around it. See how I put the absolute value in the beginning? To make sure that b turns out to be the principal square root. We've been doing principal square root, right? And Maura told us that if you take the square root of b squared, it can be positive or negative. But because we've been answering with the principal square root, we want the positive answer here. Well, y squared is always going to be positive. So Alex is absolutely right. There's no need for the absolute value when it's going to be already. Regina?
How come you wouldn't put absolute values around just the 7?
Because what's 7? 7 is just 7.
Or like
Absolute value of 7 is still just 7, right?
it's variables. You have some
Correct. It's only variables and it's only the square root of x squared. That's the only time you're going to do it. Write yourself a note if you want, so you don't have to worry. If you want to just memorize that whenever you do square root of b squared and you're simplifying, it's really the absolute value of b. It's only with a square and a square root, okay? that we're going to see. I shouldn't say only, because there's going to be other stuff later. How about part C? How about part C? This is a messy one for sure. How do I start it, at least? Give me a beginning point. When you see a fraction, what can you do with the radical?
You can like separate them.
Okay. I agree. So we'll start with that. I agree. Yeah. Well,
Can you cancel out roots?
yeah. So what do you think?
It would be, you can cancel out the 3 with the cube sign over the y, so it would be just y on the bottom.
Does everybody see that part before we go further, right? The cube root of y cubed. And don't need the absolute value there. And don't need the absolute value there. Because whatever this actually is, I'm going to take the cube root. It could be plus or minus for this, because the odd numbers could be both. But for even numbers, it has to be a positive number in there. Mark, go.
And then on the top, you would cancel out the 3 on the outside, and the 4 would become 2. So it'd be w squared.
You need to break the w into 2 parts, remember?
It would be 3 and 1.
Yeah, you got to do it this way, okay? So you have to break it into a perfect cube because the index is cubed, or the index is 3, right? When the index is 3, the exponent needs to be divisible by 3. 4 is not divisible by 3, so we break w to the 4th into w cubed and w, and then these can be reduced here. Okay? So the final answer is going to be w over y times the cube root of w. See how I'm going to write it? Notice how the way I write this, I write things as coefficients. They make more sense that way. This becomes a w, this is a y. W over y is like a coefficient. And then that's multiplying this term, so I can just tack that on here.
Why wouldn't you keep the cube root of w on the numerator about this?
Is it the same thing? Think about it for a second. If it's a numerator, you're just multiplying the numerator by it. If it's here, is it really over 1? And then doesn't it technically just put that in the numerator and y times 1 is the denominator? So the traditional way to write things when you have fractional values that are separate is to bring the things out like this by themselves and leave the root by itself alone. It's 6 and 1/2 dozen. It's right either way. But you're going to see it traditionally written like that. That's why I'm just showing you that. But you could leave it up top. Absolutely. Absolutely. Okay. How about number 9? Jeez, I keep using the number in the front. I did that with 49. How about part D? How about part D with the number 9 involved in it? What should we do here? There's a very common mistake that I hope we don't make. And you were about to raise your hand and you said, "Ooh, I can't do that. He said we can't do that." And remember. The common mistake would be to apply the square root to both of these terms separately, right? The common mistake would be to say, "Oh, this is really just square root 9w squared and square root 9u squared." Why can't you put the square root around them separately?
So there's a plus sign.
Yes. When there are factors, look what I did. I took this and I broke it into this, right? That was nice because they were factors. But when they're not factors and they're addends, we cannot do that. So what do you think we should do? Regina, go ahead.
Can we do the square root of 3w plus 3u and then just square that?
No, but that's a good try. I like it. She said the quantity 3w plus 3u squared, but that's just 3w plus 3u times 3w plus 3u, which gets foiled, and then there's a middle term, right? So it doesn't work. But that's a good idea to start. Sebastian?
Can you factor out a 9?
I would take out a 9. I agree. Remember, don't forget about your GCFs. Everybody forgets about GCFs all the time. But now, we have factors. 9 is a factor of w squared plus u squared. So I can break the radical up around each factor, and it becomes this. I'm allowed to do that. I cannot put the radical around the w squared and the u squared separately, though, because there's still a plus sign there. Because this was a time symbol right here between the 9 and this entire expression, I was allowed to separate it. Root 9 is just 3. Okay? Very good, Sebastian. Hold on. How about the last part? Who went ahead and already has it? I saw a couple of you writing ahead. Part E, what do you think we should do? And if you're stuck, think about what you would do whenever you have a trinomial. What would you do? Try to do what? Factor it. What does it factor into? What do you got, Alex? What do you got? What does it factor into?
It would be
What multiplies to give you 36 and adds up to 12?
6 and 6.
Don't help him. Let him figure it out. It's all right.
Sorry,
Brain farts, but that's all right. Okay. Now, follow-up question. Why is it convenient that it factored into this?
Because together they're squared.
Together that's squared, isn't it? That's the purpose. If they were separate factors, you can't take the square root of each of them because what is that going to do? It's not going to reduce. So this becomes this, right? And then as a result, when I take the square root of a quantity squared, it's just that quantity with the absolute value around it. Okay? Yeah, more.
How come in part D you couldn't do like 3 and the square root of, and then 3 times w plus u? You couldn't get rid of the square root in the final answer.
So right here.
Yeah,
So 3 is a coefficient on the outside.
yeah. So
That cannot be multiplied into the
no,
inside.
I know, but like when you have the square root sign on the outside, and then the w squared and the u squared, you can't eliminate that with the radical.
So why can't you reduce these, but you can reduce this?
No. Just why can't you reduce the w and the u to 3 times w plus u, because you can't.
Again, there's a plus sign here, right?
Oh.
The only time you can break up a radical to both parts is when they're factors. That's why we factored this, because now 9 is a factor of the whole thing. So I can put the radical around each of these separately. But when there's a plus sign, you can't put a radical around them separately. So there's no way you can get w or u. That cannot be reduced any further. Okay? It's a good question. It's the same concept as kind of what we talked about with canceling factors in the quiz today. Right? It has to be factors for you to cancel. You can't cancel x squared over x squared if there's a plus sign. Same idea is applied. Yeah?
But if you write it like that, are you technically multiplying 3 by the
That whole thing. But you can't put the 3 on the inside. Remember, 3 is on the outside. Outsides can't go into the insides.
You couldn't put in parentheses w plus u.
No, because again, he just asked that question. You can't take the square root of that quantity because it's a plus sign. Here, let me prove it to you, okay? Let me make more sense. Watch. Do this with me, please. Square root of 9 plus 16. What's the answer? 5, right? Everybody, the answer is 5. It is right. It's not a trick question. The answer is 5. 25 root is 5. So do your way. What's the square root of 9? 3. Square root of 4, 16. 3 plus 4 is?
7.
Is 7 5? So do you see what I mean now? Does that make sense? The two of you, the same question. You cannot take the square root of each of these individually. You can't do it up here either. So you're never going to get to w plus u from that problem. Okay? It cannot be done. You can't go like this. Okay? That is not the same thing. You can't do that. Good questions, guys. These are the questions I want to ask. Very good. Let's take the next one here. We're going to talk about rationalizing the denominator. By the way, let me quickly, I put this up here. This technique is useful still because you are going to take calculus and it helps you to reduce when you need to simplify things. But, it was introduced because calculators weren't around and nobody ever wanted to do a radical on the top and the bottom because you had to look up the radicals in tables. When I wanted the square root of 2, 1.414, and there's a bunch of other decimals, we didn't have calculators, people didn't have calculators when math was introduced. So as a result, you had a table of all the square roots, literally in the back of your textbook. So if you had a problem such as this, it's not reasonable to find the root 3, the root 2 in the back of the book, and then have to divide these wild decimals, right? Imagine this decimal. These are going to be decimals that go on forever. Both of these are irrational. So I'd have to take an irrational decimal divided by another irrational decimal without a calculator. So a long time ago, people said, you know what? Let's make life easier. Watch what we'll do. Let's get rid of one of the radicals. So to do that, get rid of the bottom one and multiply by itself over itself so that the bottom just becomes what now? What's root 4 become? Just simply 2. The bottom becomes this, which becomes this. And then the top becomes 2 root 6. This reduces to simply root 6. So instead of doing 2 root 3 over 2, we can do some little math, multiply by the denominator by itself on the top and bottom. This becomes a 3 times 2, which is root 6. That 2 carries over. This becomes root 4. 2's cancel each other out because these are factors. There's a multiplication. They cancel. They're gone, leaving behind root 6. And now I can look that up in the back of the book and have a number. You see what I'm saying? This is the reason it was introduced. It is not as necessary nowadays, but it is a technique you should know because you will use it later on in calculus and it will definitely help you there. Because you're going to do a lot of stuff with variables at that point that you have to reduce. So for now, go with me and actually learn how to do this. But I'm just letting you know that it's not as widely needed anymore because you guys actually have calculators now.
Is there, I don't know if this is the way you did it, but is there a way to change the 2 on the outside of the radical to a 4 on the inside of the radical and times it by multiply by the 3 in the radical to get 12? Radical 12 over radical 2, which is radical 6.
Yep, that works too. That's a great, that's awesome vision right there, Valentina. Here's what Valentina did, ready? She saw the 2 on the outside and said, you know what, let's just make this a root 4. Because isn't the square root of 4 just 2? Right, everybody? Root 4 is 2. And what's root 4 times root 3 give you? Root 12. This is root 12 over root 2 is just root 6. Awesome. I like it. Really good. There's not always going to be a coefficient here, so it won't always work, to be honest. So you have to still understand how to do this. But that is a great alternate way. I've never seen that done. It's a great alternate way to do that. Awesome. See if that'll work. It'll probably work in a couple of these, but not all. Like, for example, part A, you can't do that now. You know what I mean? Unfortunately, it won't help us. But in that case, it definitely did. So for part A, let's write it as root 7 over root 3 to start. And then to rationalize, we just multiply by whatever the denominator is over itself. Oops. Why am I allowed to do that? What's root 3 divided by root 3? What is it? What's root 3 divided by root 3? It's 1. You can multiply any number by 1 and its value does not change. So mathematically, I am allowed to do this. And this becomes root 21 over 3. And that's it. You can't go any further. Can 21 be broken up into anything? No. And the bottom is root 9, which becomes 3. That cannot be broken up any further. So you leave your answer like this. But this is now considered to be in what we call rationalized form. When you hear rationalize the denominator or rationalize the expression, this is what we are referring to. How about part B? Again, do this every time if it helps. What do I multiply in part B, Mauro?
The square root of A over the square root of A.
Very good. Numerator becomes just root 3a. Denominator becomes the square root of a squared. The square root of a squared is just a. And we'll throw those absolute value around there again, right? Just to reiterate, remember that. Can I go any further? No. Because look, this root 3a is under the radical. This a is outside the radical. So these cannot cancel one another. But this is considered rationalized form because the denominator no longer has a radical in it. How about part C? This is really the tough one, actually. Anybody have any idea on part C? What do I need my exponent to be if my index is 5? Again, if my index is 5, what do I want my exponent to be? 5 or 10 or 15 or 20, right? You want your exponent to be a multiple of 5, so you can take the exponent and divide it by the index. We've shown that rule a couple times now. So how do I make this a 5?
C to the third.
Multiply by the 5th root of c to the 3rd. Don't forget that phrase, right? So let's multiply by the 5th root of c to the 3rd over the 5th root of c to the 3rd. That will give me a numerator of 5th root c to the 4th over fifth root c to the 5, which becomes just c in the bottom. And the numerator becomes fifth root of c to the 4th. Okay, no simplification of that necessary. 1 and 3 gives you 4. 2 and 3 gives you 5. Cancel c. Try the last one on your own. Okay? Try the last one tonight on your own. This weekend on your own, rather, right? So on Monday we have section 6.3. On Tuesday we review. On Wednesday we have a test. Over the weekend, definitely finish this last RD example and do the homework. You can get a head start on the problem set if you want over the weekend.